2, 1. Okay. So welcome to Boospin Journal Clubs. It's been a while since we've done the last one. Today I will talk about the article about Skyrmion Qubits, a new class of quantum logic elements based on nanoscale magnetization. And I will start with, okay. So our work is based on the magnetic compounds in this study, but we also have some stuff to know about quantum computing because we are not interested in quantum computing, but how about using one of the most fundamental elements of magnetic memory structures, which is Skyrmion, and implement it as the quantum bit of the quantum computer. Is it feasible? Is it applicable? Can we make it useful? So I will talk about the a brief quantum computer properties and how do we use it? Why do we use it? So basically in regular electronic circuits, we use bits as 1 and 0, and they are not tunable, they are switchable. You have state 1 and you switch to state 0. So when we work with the quantum technology, quantum bit, which means that you are using a quantum computer, then your information is stored in the qubits and it is tunable, which means that it's not the discrete state of 1 and 0. So you have the blob sphere and you can tune the information with probabilities inside it. So this is how a quantum computer looks like. This belongs to IBM. It's in Germany. IBM made the presentation a few weeks ago. So this is the IBM quantum computer hardware. So why do we need quantum computers? This will be so briefly. At one side, you see that the demonstration of the two classical bits, 1 and 0, which means that you have one possible permutation. And when you have two qubits, it brings the 2n/2 possible permutations, which means that processing the information will be way too much faster, and we will have capable computers for advanced computational jobs that we make our computers do in recent days, like quantum chemistry, advanced data analysis, anything you can imagine. So things will be way faster. So this is the gates of the commonly used in electronic circuits, AND gate, OR gate, NOT gate, NOR gate. So they are basically made through by bits, and when they implemented inside the electronic circuit, they became a whole as meaning of what does a circuit do, and you want to process the information, then you need gates to be collaborated and they need to work synchronously. So when you want to build a quantum computer, that means that also your gate structure will be changed. All your logic gates will mean something else because your bit structure, fundamental bit structure is changed. So what do we actually need to build this new fundamental structure for quantum computing with quantum bits? Okay, so there's a reason why we call it quantum computation, because we are actually getting benefits from the quantum properties of the matter, like superposition and entanglement. And just like I said before, it's like classical bit is a switch and qubit is tuning of probabilities. So when you get the superposition property of a quantum material, it gets simultaneous existence of per-measurement of different states, which means that in each measurement, you can get another result. And when you get entanglement, this means that correlation of two different systems, where we use it in quantum computation as the interaction of qubits. When you entangle the qubits, you are actually entangle your bits in classical sense, and then you make two bits interact and work them in a parallel fashion. So this fastens everything else. So the ones who get the quantum mechanics 101, or maybe I'm not sure what's the class name. So at A section, you see that the harmonic oscillator with its states as the zero ket is the ground state, which means that the lowest possible state that the system can be in. So as the W01 means that the frequency you need to increase your ground state, your energy from ground state to first excited state, which is the 1 ket. And the second ket is the second excited state, and so on. So in a harmonic system, in a harmonic oscillator, these distances are the same, as you can see. You are increasing omega 10, and which is equal to distance between the first excited state and the second excited state, and the second excited state and the third excited state. All you need is the same amount of frequency increase to get the upper level. But when you get the unharmonic system, this is different. It's not valid anymore, because the amount of energy you need to boost to increase your energy level from first excited state to second excited state is not the same with the energy you need to increase your system from the ground state to first excited state. This means the unharmonicity. So why did I even tell you this? What's with this? So we are trying to build a quantum computer, which means that we will be working with qubits, which are quite sensitive in all kinds of senses. There are different qubit technologies that I will be mentioning in a moment. And qubit processing, qubit engineering is already a very sensitive job. So being sensitive means that your qubit can be breaking down in all kinds of perturbations from outside, any kinds of thermal fluctuations, any kind of electric field. You cannot even predict that. So since we are doing this very sensitive, we need to understand what switches our bits, what tunes our energy systems, what tunes our qubit. So I just perturbated my system with an energy switch, which is omega 10, and took my qubit from the ground state to first excited state. So if my system is harmonic, and if my frequency is increased once again in the same amount, then if I observe my qubit is also getting into the next excited state, this is not beneficial for me and not useful for me, since all I need is a 2 degree of quantum states. So I want to make sure that the amount of energy interval is not the same between the states. Then this will be giving me a clear view of the distinct energy states of the qubit system. So this is basically how it looks like when we lose our information in our qubit, because at the beginning you have both probabilities with heads and tails. So you can measure your qubit. It can come heads, it can come tails, it can come heads, it can come tails. So when the decoherence appears at the system, which can be any kind of noise, any kind of perturbation, since our qubit is quite delicate, then I can no longer use the quantum nature of this information, and that I have heads and tails as 2 distinct systems, just like the classical bit. So there will be no meaning of the usage of quantum bits when you have decoherence, when you have too much noise, when you have too much perturbation in the environment. So what are the companies doing for that? So there's a quantum information and quantum computation world, which is getting larger and larger each day. So some of the most famous quantum computing companies are actually working on different physical mechanisms, such as Google, IBM, Rigetti, and D-Wave are working on superconducting loops, and Honeywell and IonQ working on trapped ions, Intel Corporation and HRL working on silicon quantum dots, and Microsoft is working on topological qubits. So as you can see, these are all different physical mechanisms, but at the very core, they are after the same thing. They are after finding non-volatile, strongly correlated, and preventing the noise from outside 2-degree quantum mechanical system. This is what they're after. They are using different words, they are using different physical mechanisms, but this thing they're after is the same. So one of them is in a quite popular nowadays. It's the Microsoft's topological qubits. The reason of this is quite simple. Other ones are in need of quantum error correction due to outside of experiment upcoming noise, and then they needed the coherence fixation with lots of surface code and lots of quantum error correction work. But in Microsoft technology, topological qubits, information is encoded and it is directly embedded into a topological protection. So there is no way that you can penetrate into this topological relationship inside between qubits, and it doesn't need any quantum error correction. So it's way more healthier and quite useful for not getting another way of error correction process when you process the information. So this is really promising for upcoming quantum technologies. But as you can see, there are different ways to compute with quantum bits. So this is the list of 7 core qubit technologies for quantum computing. Superconducting qubits, semiconductor quantum dots, trapped ions, photonic qubits, defect-based qubits, nitrogen vacancy in diamond, topological non-wire qubits, which means the Majorana qubits, and nuclear magnetic resonance. And also, there are these 7 key requirements for quantum computing, which are first, long coherence time, because we need our information to be coherent, high scalability, I need to entangle more qubits to process more information, high fault tolerance, ability to initialize qubits, universal quantum gates, qubit measurement capability, and faithful transmission of flying qubits. Okay. Until now, I talked about this quantum computing station and how it works and what is the main idea behind this. So now, since we all know a little about skyrmions, the subject of this paper is basically how can we implement this topologically protected magnetic textures into quantum computing. Okay, so I just mentioned that Microsoft is trying to build a topologically protected quantum computing. And the main idea behind this is creating a topology and embed the information, code the information as the topologically protected system, whatever it is. It can be a quantum Hall system, it can be a skyrmion, it can be a Majorana fermion. It's up to the producer projects. It's not well defined, but in the end, if you protect your information with topology, you won't need any kind of quantum error correction, and your decoherence will be lesser. Your information will be highly protected, and it will be way better than the too much noisy quantum computing systems. So this the image you see is example for that. How to encode your information in a topologically protected system. Um, this is the topological qubits on torus. As you can see, it is coded with brackets. There are several different states coded into torus, and in the other side, it's a basic scheme of how to carry your information when you have a topology in the system. So this is our Skyrmion, and as we know it, Skyrmions are topologically protected systems. So why don't we just use Skyrmions to protect the information in a topological sense, and then use it as a qubit? Because we already know that Skyrmions can be useful in racetrack memories as the bits. This is, once again, I wanted to show this. And why can't we obtain this blow sphere system by using the quantum nature of Skyrmions instead of, because we know that we can obtain Skyrmions in room temperature. So what if we can use the quantum utility of magnetic moments on the Skyrmion system and then process the quantum information with this? So this is how bits, and it's already published. We know that they can be used as bits. So this very paper suggests to use Skyrmion's nature inside the quantum bit. Okay, Skyrmion Qubit strategies. So this is the, let me push this like this. Okay. This is the suggested physical mechanism in the paper, which is basically made of two layers separated with a non-magnetic layer, and two Skyrmions with different helicities are between these sandwiches. And at B section, you see that there's the blob sphere, and the main problem with this system is how to obtain each state, how to code information with using this vortex-like structure, because it's not like a single spin, you know. You can just say that, okay, this is on and this is off. So let's entangle these qubits. You can do a spin qubit, but this is not like this. This is a vortex structure, and there's different parameters that has effect on the Skyrmion structure. And by calibrating all of these parameters, you need to obtain a psi-ket, which is a quantum wave function, and with different probabilities. And you need to measure this to get the universal quantum gates. There must be a quantum measurement of this. So let's see what they suggest to do. So to use a physical system as a qubit, you first need to do the quantization, because you have to learn how it behaves quantum mechanically, and then try to get a 2-degree of quantum mechanical system to use as a qubit. So this formula, I don't like putting formulas in the presentations, but just to introduce you, this formula is basically the quantization of the Skyrmion field, where H and K are the Zeeman and anisotropic coupling, respectively, and while J1 and J2 denote the strength of competing interactions, and the A is the lattice spacing. So in offered systems, there are two types of fundamental qubits offered. I think it works. Yes, okay. So first one is the SZ qubit. I didn't want to go into quantum mechanical details, what SZ does to system and what it measures. So I will try to explain briefly. And so this gate, this qubit works as the angular momentum operator and gives the exact spin value when interacted with the scat in an S spin wave function. So when it is when they dig inside, then how to use this qubit. First, they wanted to see its behavior on magnetic field gradient and then electric field, out of plane electric field, EZ, and IH with line on top of it, and with the frequency. So as you can see, this Skyrmion offered Skyrmion structure is stable in the nanodisk. And in this picture, you can see that the Skyrmion structures are stable in nanodisks. So their translational motion is disregarded. It's not a degree of freedom for this offered system. But the degree of freedom can be used is the helicity. So processing of each magnetic moment by external parameters. And also the SZ magnetic spin angular momentum phenomena. So in here, they made it possible to learn if we can get this structure anharmonic, like we mentioned before, and how can we lift the degeneracy in energy relationships of these two parameters, because there are two parameters that affects the Skyrmion's behavior, which is the magnetic field gradient, which is supplied by the micropulses, and the other one is the out-of-plane electric field. So as you can see at the C section, degeneracy can be lifted by each of these parameters. So this is basically meaning of we can tune this qubit by using electric field and magnetic field gradient. And at the B section, you see that the unharmonicity actually exists in this energy and helicity diagram, because we know that system is topologically protected, which means that when we look at its helicity 5,0 at the bottom of the B section, system will be same in each 2 pi of turning processing. So we know that 5,0 ket is equal to 5,0 plus 2 pi ket. This makes the system protected. So at the MZ, at the D, we can see the magnetization behavior of this vortex-like structure when it's stable on the nanodisk. So another fundamental qubit behavior can be obtained with this structure is the helicity qubit. And different from SZ qubit, you can see an elliptic behavior of this Skyrmion-like structure. Magnetization is a little bit elliptic. And by the way, I also added its Hamiltonians. I don't know how many of you had quantum mechanics class, but I already had the Hamiltonians of these physical mechanisms when we measure the system with SZ and when we measure the system with 5,0, helicity operation. There are results. This is actually what we try to do in quantum computing. You get the quantum mechanical operation into a state and you get a result. So if you have the right Hamiltonian like this, HSZ and H psi 0 with a certain potential, then this means that, yes, you can use this measurement and you can do quantum mechanical operations on the state. So this is also a validation for its feasibility for quantum computing. And when we look at the B, we are observing a double well potential structure, which means that it's different from the previous gate, potential gate, SZ qubit behavior. So when we look at the behavior, it's still anharmonic, and still you need to have different values of H bar omega or from the ground state to first excited state and first excited state to second excited state. We are not interested in second excited state. They just wanted to show that the amount of energy required is not the same. And when we look at the behavior of magnetic field and electric field, it still covers the degeneracy, because when these two universal energy behaviors matching at the zero energy point, this means that you have two states at one single energy value, and this is not what we want in quantum computing, because this means that two bits actually has the same value. So this is confusing for quantum computing. And this means that also helicity qubit, when we use this skyrmion as a qubit and use its helicity for degree of freedom, it is also can be manipulated and can be tuned by electric field and magnetic field. And its Hamiltonian is right up there, right down there, and interaction of qubits. So, okay, you make sure that this Skyrmion structure can be useful for being a qubit, act like a qubit, but it's not the end. You need to interact with these qubits. You need to somehow entangle them. Maybe not physically entangle, but you need to make them speak, to make your circuit, make your quantum circuit, make all the quantum bits talk each other. So this is theoretically explained in paper. So I just wanted to show you that the theoretical outcomes. So this is the basic interaction term of two Skyrmion structures. And when you include the helicity, it turns into a Hamiltonian like this. And we also want to see its spin couplings for X and Z directions, because we are disregarding the translational motion in this Y direction. And we are interested in X and Z couplings. So this is the Hamiltonian of the interaction of this structure. So once again, the Hamiltonian means that this is quantum mechanically accessible, and we can actually measure this quantum mechanical state psi. We can create a psi with this information, this coupling, and by using the helicity or by using the spin angular momentum of the system. So this is the offered electric field and magnetic field gradient regimes and lifetimes. So table 1 is the relation between physical and dimensional parameters. And in table 2, Skyrmion qubit operation regime and lifetime. And there are some constants. And for each qubit, there are certain magnetic field and external control parameters are given. These are for proposing an experiment, maybe. I'm not sure. And I think that will be all for me. I can have your questions. Thank you.